Alright, welcome to our third class of being in fully remote. Last time we talked about a lot about caches last week. We're going to finish up on caching today, which is going to go into virtual memory, which is another way of the operating system does caching in order to support certain features like the fact that your program may use more memory than is available, or being able to run multiple programs at the same time whose sum of memory is actually more than what is available. Before I continue, I do want to make sure it's crystal clear. Please go through and learn how these cache systems work. It is imperative from both a security and performance perspective how caches have affected the machines that we have in front of us. Performance-wise, hopefully you've seen that it will improve many factors of performance, and security-wise, when we get to Meltdown Spectre, we'll show you that the fallout of these performance enhancements has led to some very serious security issues. So I'm putting this up class problem 8. It's a good one because it's two-way associative. No write allocate, no write back. If this is too confusing right off the bat, please go back and review the slides and see if you can preview how these cache systems work. Let me go ahead and move forward just a little bit. We integrated the caches. So now that we've talked about caching, one thing we want to talk about is, again, caches with SRAM. It's big area-wise for each memory cell, but it's a lot faster, and so if you have a very small amount of it, it's still small and fast. DRAM, each cell is a little smaller, but it's a lot slower, and then magnetic media or even SSDs, it's even more compact, but accessing it's even more slowly than the previous three. Alright. So there's a couple of problems that we haven't talked about when it comes to memory. DRAM is too expensive to buy many, I will say terabytes nowadays. Yet we want our programs to work even if they require more storage than we bought. If your program requires a terabyte of memory, we don't want it to run or fail just because you only have 4 gigs of RAM. No one wants that. We don't want a program that works on a machine with 512 megabytes to start working if we try to run on a machine with only 256 megabytes of memory. Also, the other problem is we may want to run more than one program at a time. So if your machine has 8 gigs of RAM and you have 10 programs each that consume 1 gig, you want all 10 to run, even though the sum of the memory they consume is greater than the capacity that you have. So we need to come up with a way to solve this problem, namely that we want to utilize more memory than we actually have available. Solution 1. Leave the problem to the programmer. Classic solution. Hardware is like, whatever guys, software, you got this. We assume the programmer knows exactly how to configure the machine, so they either need to make sure the program fits in memory or break up the program into pieces that do fit and load each off the disk when it's necessary. This is not actually a bad solution in some domains. For example, your consoles, PlayStation 2 and some of your cell phones, even the modern consoles do this to an extent. This is not bad because in general when your console you're just running one program at a time anyways, so this is not too bad. Solution 2 is called overlays. This is not what anyone uses nowadays, but I wanted to show you the interim solution before we came to a final one. Basically, the programmer is still in charge of doing it, but we're going to give them a little library tool in order to help them out. So the idea is that we go over here that the operating system may overlay memory into 3 different chunks, that color, that color, that color, and each of these columns might be a program. So one program may require all 3 of them, one may require this one and that one, and one may require just this over here. So the idea is that if we need to run our program, we need to access this memory, but we check and someone else currently has it, well, you need to offload theirs and then load yours back in. Just a little memory to help them out. But this is not what we do because this actually ends up being too complicated and way too cumbersome for a program. So solution 3 is we build new hardware and software that automatically translates each memory reference from virtual address into a physical, aka we add a level in direction. The idea is instead you're going to write your program as if you have all the memory, and then we're going to have the hardware and operating system. Notice that this is now a hardware and an OS solution, so there's still a software solution, but the application program doesn't need to know. We're going to have a hardware and software that goes ahead and does the translation in the background. How is this going to happen? Well, when you do your virtual address, this is also called the architectural memory model, where you're just asking for a piece of memory. The operating system and the hardware together are going to translate that into what physical address actually exists. In other words, you're going to say, just give me this piece of memory, and then the hardware and the OS will do that translation for you. So, for example, you might say, yeah, just give me my memory at this address, and then the OS can say, well, we went ahead and put your memory at this actual location, so you're going to read from there. Your software doesn't know this because your software is only going to work with these addresses, but it's going to translate to this physical address under the hood. Or it may be on the disk. Who knows? But the virtual address is the same because that's what the programmer cares about. The OS and the hardware are going to do the translation for the programmer. So virtual memory lets programs see a memory array larger than DRAM. Virtual memory enables multiple programs to share physical memory without knowing that the other programs exist. This is called transparency because you're just reading and writing to memory and worrying about one program modifying another, because the operating system and hardware are going to provide protection between one program and another. Again, if I haven't made this self-clear, virtual memory is what all our modern systems use. So solving this is something done by hardware and the operating system. So the hardware is used to keep for speed purposes, software is for flexibility, and that some problems just don't need to be solved in hardware. And if it doesn't need to be solved in hardware, you don't, because that always consumes a lot of area and is very costly. So virtual memory, well, instead of having a cache that caches main memory, we're going to have main memory act like a cache to the disk. Alright, but we want to minimize disk access, so we can either one, have a lot of memory, that would be great, but not always practical. Exploit temporal locality, so we want to have a fully associative cache because a direct map would not be able to utilize all the memory. Exploit spatial locality, aka we want to make our block size big. Notice that in a cache it was from 32 bytes to 128 bytes. I can tell you here that Linux uses a 4 kilobyte page or cache line, so to speak, for its virtual memory. And write back or write through, well, we don't want to be writing to the disk, so we want it to only write back when we have to. So instead of calling it a cache block, we're going to call it a page. Let me pause here for a moment. Virtual memory is a caching system. We're just going to use different names for it. So instead of having a cache block, we're going to have a virtual memory page. So just like with a cache block, you have your tag right here, and you had your block offset. Now we're going to call it the page offset, and this is your virtual page number. A cache miss is now going to be called a page fault. Yes, I know these terms are now completely different words. Why do people do this? I don't know. Probably just to make your life difficult in this course. I don't know. They are generally handled by an exception to the operating system, so when a page fault occurs, the hardware, the hardware throws an exception and says, hey OS, we got a page fault. How does this happen? Well, on your left, this is your virtual memory starting maybe at 0, and you've asked for all your different bytes and your function is growing and shrinking. But inside of the operating system and hardware, there's this translation that takes your virtual address, either maps it to some part in physical memory or on the disk. Notice that each of these sections, aka a page, may map to different parts of the physical address. It may not map into any particular order, or it may map to the disk, or it may just be labeled as doesn't exist yet, in which case the operating system and the hardware need to allocate it later. So how is this set up? Well, this is a bit complicated. You have your page table register, which actually points to where the page table resides inside of main memory. And right here is the address that your program has. So I want something at address blah, 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 blah. Well, it takes the page offset and sends it over here, because down here is going to be the final physical address of what we're going to load. The virtual page number indexes into the page table and then finds the page number and then maps it down here. So, think about this. This is a cache, this is not the cache yet. This is a type of cache which takes the page, your virtual page number, and translates your virtual page number or your virtual address into the actual physical address by indexing into a page table which is inside of main memory. So in other words, let me flow this from beginning to end. Let me see, do we have a picture of that? Excellent, we have an example. Let's say you want to load a memory address inside my program 00040F3. Your program is hard-coded to load this address at this point. That's how it is. The hardware and the operating system combine, say, okay, well, we're going to chop off this section, send it over here, because that's just like the block offset or the page offset. This value is going to be indexed into the page table, and currently your 4 is allocated at physical address 020C, so we're going to copy that down here, and now the physical address of the piece of memory you want is located right here. That is how the translation is done, similar to the caching system. Again, if this is confusing, please review the cache system before you look at this. Another example might be that it's not valid. Notice we had that bit before. Here it was valid, and that's because we knew that this piece of memory was in main memory. Now we're going to say it's invalid, so we're going to say it's a disk access. So it's what's called a page fault. How do we do this? Well, we haven't taken operating systems yet, but what happens is we stop the process, aka your program that's running. We pick a page to replace inside of main memory. We write that page back to disk. We say, hey, you program over there, you haven't used this page in a while, and they're evicting that to disk. We get the reference page number, we update the page table with that address, and then we reschedule the process. All that has to occur on a page fault. Hopefully you can see that that is a very expensive operation, in which case we want to avoid this at all costs. But how do we find it on disk? Luckily, this is not a hardware problem, so we don't really care in this class because the operating system does that for us. Isn't that sweet? Well, how does the OS do it? Well, we'll talk about it real quick. In a Unix or Nix or any Linux type operating system, there is a swap partition that is specifically designed in order to load and unload these page tables. Great! Otherwise, you might have Windows which like to make a page table entry inside of C or D drive. Sure, whatever. What's the size of the page table? Well, how big is the page table entry? Let's say that we just have a 32-bit address. We'll talk about 64 later, but you'll see how this is a problem. The machine has 1 gigabyte, that's 2 of 30 bytes of physical memory, because that's how much RAM it has. If we use a page size of 4 kilobytes, very common, to the 12th, then the physical page number is 30 minus 12, which is 18 bits, plus another valid bit, plus other stuff, read-only dirty. Let's just say it's 3 bytes. How many entries are there? Well, if we have 32 minus 12 is 2 to the 20th, or a million entries, the total size of the table would be 1 million times 18 bits, which is about 3 megabytes. So 3 megabytes of your RAM is just being spent having this page table to support virtual memory. How can you organize the page table? You can make it a contiguous 3 megabyte region of physical memory. And for modern systems, that would probably be okay. But hopefully you can see with the 64-bit system that this is not going to be acceptable whatsoever, because now instead of 30 minus 12, if you have, let's see, 16 or 64 gigabytes of RAM, this number is going to jump up into megabytes, possibly close to a gigabyte, depending on what's going on. So we could use a hash function instead of an array. It's slower but less memory, and this is an idea but not something we want to use, because when you take operating systems, for those of you who's going to take operating systems, a hash table is way too slow. So we just page the page table. In other words, we add another level of indirection. So we have the super page table and the virtual page table. Let me show you how this looks, maybe, or maybe not at all. So you don't get a picture today. Sorry, guys. But the idea would be that you take maybe this section right here, which would go into a page table, which would point to another page table where we take the next section, and that's the index in there, and that would produce our last physical address. No picture for you today, guys. So putting it all together, what happens? Well, this is what happens when your program loads. It asks the operating system to create a new process. It says, all right, let me allocate all the data necessary in order to start running your program. Let's construct a page table for this process. Mark all the page table entries as invalid with a pointer to the disk image of the program. That is, point the executable file containing the binary to the file, but we haven't loaded in memory. Run the program. Well, when we run the program, the first thing that happens is a page fault because there's nothing loaded in main memory. Yes, this is exactly how processes work. How do we replace it? Well, we want to always replace the least recently used. True LRU is expensive, but it's a heuristic, so we usually keep a reference bit and clear it occasionally, then pick an unreferenced page to evict. This is not too important because you'll go more into it into operating systems, but just keep in mind that we do a pseudo LRU replacement strategy. So what's the performance of this virtual memory? Well, it turns out that this is actually a big hit. Because let's say we want to read from this address. Well, then we have to access physical memory. First, we need to get the physical address, so we must access the page table in memory. That's another read. Then we must get the data. So that's a load becomes 2 reads, and a store becomes 1 read, and then a write. So now every memory access is now at least twice as slow. And we already talked about or showed you that memory accesses are really slow for this machine. In other words, having two memory accesses or slowing the performance by twice as much on the slowest bottleneck of the system is completely unacceptable. So how do we fix this? Well, we have the pages which act like a cache, and we've already cached the cache with the super page table. So if we've already cached the cache and the cache is still too slow, what do? Give you a couple of seconds because I've said the word a lot. We cache it. Again, I'm not making this up. We fix this problem by avoiding main memory and translation. We use something called a translation look-aside buffer to cache the memory dedicated that we've already looked up. So instead of having to constantly look at the page tables, we're going to cache the recent memory access that we've had to the page table in order to increase the performance of doing our virtual memory translation. So there's another cache inside the system, and it's called the translation look-aside buffer. By the way, V to P is virtual to physical translations. So the TLB, it is a cache. You take the virtual page, you see if it's inside the tag, and then that gives you the physical address afterwards. But the question is, where do we put the TLB? We can put the TLB lookup in the pipeline after the virtual address is calculated and before main memory. This may be before or during the data cache. Without a TLB, we'd have to perform this in a later stage. Okay, sure. Virtual memory translation. By the way, this is virtual memory, not virtual machine. Virtual memory. The page data location, we have to keep it. Is it physical, disk, or uninitialized? That's another couple bits. We do need to keep track of access permissions because if they're not allowed to read from a certain page or write to a certain page, for example, if two processes are sharing memory but only one process should be writing to it, we need to keep track of if they're allowed to read or write to it. Also, if we need any dirty pages to write it back. And of course, anything to determine LRU. So, placing caches, now we have two addresses. Remember, we have physical and virtual. Do we cache the virtual address, which gives us faster access, but it's more complex, or do we cache the physical address after the virtual machine translation? But that's inside of our data cache. Sorry, I did not make this clear. The data cache. Is the data cache doing the virtual physical address or the virtual? Basically, the long and short of the story is it depends. We already talked about that, talked about that, talked about that, talked about that. Hey, look, slides that happened again. Okay, so let's go ahead and picture our physical caches. How does this look? Well, this is going to be kind of complicated. You have a virtual address, which comes from the process. Virtual page comes into the table, the TLB. Hopefully it finds it and gives you the physical number. And then that page offset comes down here. Now in this physical address, it's chopped up again in order to go to the cache, the block offset with the tag, the index and the tag. And then you give it a bunch of compares and hopefully you get your data. Wow, that was confusing. That was probably confusing, but again, make sure that you understand how regular caches work, and then the TLB should make at least some sense. Alright, virtual address caches. You can perform the TLB lookup at the same time as the cache tag if you're using virtual, but the only problem is you might have some aliasing issues when you do that. Great. We're going to skip that for now. OS support. Keep in mind that in order to edit the page table and update the values, this can only be done by the executive or the super user or kernel level of permissions. So inside of the processor, it does have two modes. One is called super user or kernel mode, and the other is called user mode. So kernel mode is allowed to do everything. User mode is basically not allowed to do anything except for inside of its process. And if it wants to interact with some physical device, it has to interrupt and talk to the kernel. So let's do a full example, because I think a lot of this has gotten very confusing. This example does not have the data cache, but it does have a TLB in the page table. So step one, we want to read the executable header of our program. Excuse me. And our program looks like this over here. Text, and maybe some static data. We allocate a page table that data 1000, aka this guy here, 1001, 1002, but it's on the disk. So it's disk 1000, disk 1001, disk 1002. I accidentally said data beforehand. My apologies. These are the references that are about to come out of the program. First off, we ask for 0. Is it in the TLB? Nope. By the way, I'm doing a 2-entry TLB in order to make this simple. Obviously, this TLB would be much bigger. So when that happens, it's a page fault. We have to go, page fault, because it's on the disk. And then we have to go ahead and read the text into memory. We put the entry into the TLB, and in the page table we mark that any address starting at 0 goes to M1. Perfect. Now we go to 004. It's a hit because it's in the TLB, so we read directly from memory right in here somewhere. Notice we did not have to go to the page table. 07 FFC, is it in the TLB? Nope, it's a miss. So we have, unfortunately, there's nothing mapped to it. So we don't even read from disk, which is nice. Basically, this is just saying that the processes need a piece of memory, aka when you say malloc or something. So it says M2 is right here. We'll set it to maybe some zeros and put it in the page table there. Now 008, it's a hit, so we go ahead and read directly from memory. And 2134, it's a miss, so we need to evict something. We'll evict, we go to the page table, sorry. It's a miss. We go to the page table, it's on disk. We have to load M3, it's the iStatic, maybe some static variable that we need. And then we are done. If you have questions on this, again, ask on Discord. I'm sure I'm going to have plenty. So how do we do multiple processes? Well, virtual cache support multiple processes. Basically, every time you do a context switch, you can either flush the cache, aka clearing out the translation local site buffer, and it'll be populated as necessary, or you can put in process IDs if you want. Can we run 2 programs at the same time? Each processor has its own cache. Why does it have its own cache? Well, because so we can run 2 processes at the same time. Problem is, are we sharing code? Well, if you're sharing data, aka code, DLLs, you mark it read-only, you don't really have a problem because you're not writing to each other, so that's okay. The problem happens if you're trying to write. And if I had the board, I could show this to you real quick. But the idea is that if you have 2 cores or 2 processors, they each have their own data 1 cache, which are trying to reflect something in main memory, and one person writes to their cache and the other process is supposed to have that memory too, you now got a problem because one cache has a piece of data, is representing a piece of data differently than the other. So you either need to invalidate the other cache or update the other cache as needed. And that's called snoopy caches. Luckily for y'all, that is an advanced architecture subject, so we will not get to that in this class. Alright, well, I covered a lot, and I'm sure I went to that way too quickly. So please, please, please go on Discord or email me if you have any problems. I highly recommend Discord because so far every time I've opened up my email, it has essentially exploded, and I know for a fact that I simply have not been able to get to all the emails. Also on Discord, I've noticed that after Friday, my Discord is still blowing up with messages. Guys, again, Saturday and Sunday, I'm just not going to be able to get to it, but Monday morning, I will start looking at Discord and whatnot. All right.